we will see what are the characteristics of the MOSFET as a switch and as an amplifier. Okay, so here you see the screen, on your screen what you are visible. So this is the circuit that we are going to use for this lecture. So now I want you to identify what is the role or function of this MOSFET during in this current bias condition, or in this condition whatever it is. So the resistance value given is 1K. So that is having an current that is flowing through it, and we have an input and the output information present. Okay, so let me give you two additional values. So the additional values will be what is VT. VT 1. Round figure. Let me give it as 1.5 volt, and let me give K equal to half mu n Cox W over L equal to 0.75 milliampere per volt. Correct? If I want you to find out what is the characteristics of the MOSFET in this particular case. So what do I mean by characteristics is, you need to find out what is the operation of the across all the temperatures, sorry, across all the voltage supply rates. For example, from 0 to VDD. So if you give an input Vi, how does this MOSFET behave, and in what all regions it behaves? So that will be there. So let's see what it is. So why don't you start off? This is continuation to the assignment. Trinath, I have not yet sent a reply to your assignment. I will probably do it by after this class, because I was held up with other work today. I have made the comments already. I have to just send you the email. So I will just do that. Or if you can give me some time while you guys are solving this problem, I can send you the response.
It's okay, sir. Anything is fine for me.
So in that case, I will send it after this class, so that I don't get distracted with the attention. So, okay. So now I would request you to all turn on your videos, cameras turn on, so that we can see your text, or you can work it out, the equation, and as and when you can talk on saying how you are going to solve this problem. So the people who have attended the answered the questions in the assignment, this will be under 1 minute. You will be able to solve this. Okay, if you have begun, let's go ahead. So what I want to know is, what is the region of operation? Region of operation, okay, for the MOSFET, and what are the VDS and VDS values and ID value. Input varies from 0 volt to 5 volt. So let's solve this equation as a first step of, because we will learn by doing problems this way. if anybody has started solving or reached the phase, you can show. I think Kalyan is going fast. Kalyan, I'm only able to see right half. Left half is entirely open. So, okay, great. Yeah. Okay. If anybody has got some kind of, you can start discussing. Let us go through.
Hello, sir.
Yes, sir.
Sir, one condition is that we can take VA should be greater than VT for the transistor to on. That is the first condition.
Which,
Hello.
yes,
Hello.
okay. Go ahead.
VA should be greater than VT. That is the
Are you
first
able to hear me
condition.
till now?
Yes, sir. Some breakage is there, but it is not a problem, I guess. I'm able to hear you.
Okay, great.
If VA is
You
greater
can
than
keep
VT, then
continuing. I'm able to hear you.
if VA is greater than 1 volt, then it will be on. So we have to take two conditions.
Okay.
One is we have to write
Mhm.
equation VDS should be greater than VGS minus VT.
Okay.
There
Okay.
in VDS we can write VD as 5 minus ID into 1 kilo ohm.
Okay.
Hello.
Yeah, good. Keep going on. Going on.
Okay. VDS should be greater than VGS minus VT. So
Okay.
VDS we can get as 5 minus ID into 1 kilo ohm should be greater than VG minus VT.
Okay.
So in ID we can keep the linear equation because actually we are considering this is in a saturation region. Then we will get the value of VI. What is the value of VI should be taken into account.
Okay. Mm-hmm.
And if it
Okay.
is greater than something, it will be in saturation at that point. And the remaining thing, if it is
Okay.
less than that thing, it will be in linear. Like that we can conclude it.
Okay. So I will need to know what are the input values for which it will be in each of these ranges.
Yes, sir. Yes, sir. This is a quadratic equation. I'm solving it.
Okay. Cutoff, linear, and saturation. So what are the other equations that we have? Governing equations. It is VDD minus R into ID. Okay. R into ID equal to V out. That would be 5 minus ID into equal to. So okay. Yes. So how do we go forward? Yes, Srijan, go ahead.
Sorry, if Vi is greater than 3 volts,
Vi is greater than 3 volts, okay.
then it will be in saturation.
Vi is greater than Vi. Okay.
And if it's
So
less
how
than
did you
3
get
volts,
that?
that one, actually I have taken one condition, sir, that VDS should be greater than VGS minus VT.
Okay.
In that I placed that VDS value, and I found for VGS condition.
Mm-hmm. What is the VGS value for first condition? Okay, what is the current condition you're saying? Tell me what is the VGS? Whatever you have described, that you tell me.
Yes.
What is the VGS value?
Okay, first one thing is confirmed that VGS should be greater than VT, then it will be on. VGS value should be greater than 3 volts to be in saturation.
VGS will be greater than 3 volt for saturation. Okay.
Yes.
VGS
And
has
if it
to
is
be
less than
greater
3 volts and
okay.
VT and VGS less than 3 volts, then it will be linear region.
VGS is less than 3 volt linear region, okay.
And it should be greater than VT also at the same time.
VGS has to be less than 3 volt and less than VT, yeah?
And greater than VT. And greater than VT.
Okay. VGS has to be greater than VT, okay. So this what is this range?
Yes, yes.
This is going to be linear region.
Linear region, yes. This is what I get, sir.
Then cutoff region would be?
Cutoff VGS less than VT.
So VGS less than VT equal to 1. 1 is cutoff. Okay. That's right?
Yes, sir, yes, sir.
Okay. Very good. Let's now.
Let me confirm from your side whether these conditions are correct or not.
Okay. Now during cutoff, okay, what is V out?
During that V out will be 5 volts.
So let me make a small table here, okay, just so that we know in which direction to go. So the table I'm trying to make is what is V in and what is V out, and what is the range in which it is. So what you say is if V in is less than 1, if V in is less than 1,
V out will be 5 volts.
V out will be 5 volt. And the range is cut off. Okay. Then how did you get this 3 volt?
The 3 volt, I put in that current equation, sir, that VDS should be greater than VGS minus VT, right? That is condition for saturation.
Correct.
There I have kept ID as saturation current equation. There we can able to find VGS.
Okay.
Like that I found like that.
Okay, fine. That's a nice, correct way to do that. Okay, so what is the output voltage when V in is between 1 and 3?
That thing exactly we have to know sir values. It will be in range, I guess, not in particular value.
No, you give me an equation. There must be a correlation
Equation. Okay.
with V out and V in as variables.
Okay.
Okay. So you know that this is going to be in saturation at least, right? So
Now it is in linear. Second condition.
linear, huh?
Yeah.
Are you sure?
Mm,
Sujan, can you show me your equation? I would, yeah, exactly.
Yeah, my VGS is in saturation, right? So for VGS less than, VGS greater than 1 but less than 3. For in that range, my device is in saturation.
It's in saturation, correct.
Yes.
okay. Maybe I have
So
said this way that.
So Kalyan, you had almost completed a lot of things. Are you able to find out what is the equation for that? Robin. See, we will use this standard equation here. Okay. What is V naught? What is V output? V output is VDD minus R into ID. That is one. So in saturation, what is the current equation? Use that. ID equal to K times Vs minus Vt. VGS minus VT whole square. So this is for saturation. And ID is equal to times K VGS minus into VDS VDS whole square. Right, this is for linear. So in the saturation region, add this, you will get ID value. After you substitute ID, substitute back into the V out equation to get the output. So V out equal to VDD. So VDD is 5 minus IDR. So R is 1K into ID. So VGS is equal to V in. So you will know V in value and ID will have, okay, so times V in minus VT the whole square. So that is ID.
Hello, sir.
Yes.
Small correction. VGS greater than 3 volts, that will be in linear,
Hmm.
and this range will be when it is in less than 3 volts and greater than 1 volt, it will be in saturation.
No, yeah, that is what Susan already informed.
Yes,
Okay.
yes.
So that is already in saturation. So by completion, linear should be the rest of the value. Okay. I'm assuming that is going to be correct. So 3 volt less than V in less than 5 volt. Okay. So now I want you to tell me what are the V out values or V out expression for saturation region and for linear region. Okay, can at least somebody tell me what is the current value that you are seeing, so that let me put another column where
The
we will see. Yeah, so cutoff region there is no current flowing, so ID is not there, so that is understood. Current ID, okay, so cutoff it is 0. Ideally no current should flow. Okay, then what about in saturation region?
the current is 1.5 milliamperes.
Is it going to be
Maximum
fixed?
ID. No, that is the maximum value.
Okay, so
That
what
is
will
the
be the other
maximum value.
range?
The minimum,
ID
I have just calculated the minimum and the maximum. The minimum is 75 microamperes.
75 micro, okay. 5 microampere. So that is at V in equal to 1 volt. And 75
I have
microampere
taken
and
it as
the
V
other
in
one
is equals to 1.1 because otherwise it will become, the whole term becomes 0.
okay, fine, fair enough. So 1.1, so 75 micro to
1.5 milli.
1.5 milli. Now ID is got, so now tell me what is the output values that you are going to get.
So the output for maximum current is 3.5 volts.
Output for maximum current is 3.5 volt, okay. 2.5 volt, and the other side, how much is it?
It is 4.925 volts.
4.925. Huh?
Yes.
Great. So now what is the next value?
That I'm calculating right now.
Okay. So anybody else has done it so that we can check?
No, just at hello. Hello, am I audible?
Yes, you are audible, Robin.
Just at 4 volt I calculated it was coming 1.067 volt.
No, we need the full range.
Full range.
So from
That
full range, 3
that
volt to
I-
5 volt, we need that full range. Along with that, we will need the current value also. So, so the reason for doing this one is I'll do, yeah.
my network goes.
Well, no problem. You can go in and come. The thing is, when you're doing problems, right, network may not be needed. Once you get the result or something, you can get back inside. Because learning is already happening. No need to worry. So this will be V in volt. Okay. V out in volt. Five. 1. Okay. So these are the current values that you are going to see. This is 3.0. Okay. So for V in equal to up to less than 1 volt, output is 5. So let me define the outputs also. Meanwhile, we will keep calculating 5, 2.5, little above maybe 3.5. Okay. V n equal to less than till less than 1, V out is 5. Okay. Then it goes from 4.9 to 5 to 3.5. This range. Let me assume it is a straight line. Okay, so this is the third one. So what is the last range between 3 to 5? So we need to fill up this graph. Okay, so that is why we want that last value.
Sir, for last value, how VD we have to take it, sir? Linear region.
VD will be V naught, right?
Yes, yes, we know.
So anybody was able to? At least can you tell me what is going to be the voltage equation in the linear mode? So that at least let us see if at least till that phase if the thought process is correct.
So what I
Okay, are others? I am unable to hear Sujan. Are anybody else able to hear me?
Yes, sir. I'm able to hear you.
Yes, yes, I am also.
Okay. Okay, great. Okay, looks like Srijan is probably some network issue might got. Anybody else who's able to get this problem?
Okay, V naught. The equation is V naught equal to
Mm-hmm.
5 minus 2k. Hello.
Yeah, tell me. Go ahead.
5
5
minus
minus
2k
2k.
into VGS minus VT into V naught minus V naught
Okay.
square.
Into V naught minus V naught square. Okay, correct.
Yes. From there we have to put this VGS values and we have to calculate V naught.
Yeah, so no, you have got V naught. Now, what will be the you got V naught on both sides of the equal to sign, right?
Yes.
Equation.
Yes. Yes. Yes.
You need to combine all of them and then bring it out. So since it is a V naught square term, you will get a quadratic.
Quadratic equation.
Hello, I
So
have one doubt.
yeah, it will be a quadratic equation. Can somebody share what is the quadratic equation that you have got?
No, I have one doubt in this equation.
Yeah, tell me.
So K is like what we have taken is half mu n Cux W by L.
Right.
So why 2K is coming in ID equation,
Because there is half, right?
right? So this 2 must come with V 2 times of VGS minus VT
Yeah.
into
It should come
VDS.
inside VD inside.
Outside K will
We should get 2 inside, sir.
Yeah, correct, correct. It's not, it's only
just
k into 2. Right,
ah,
correct, correct. Yeah. Let me, I, as a habit, I wrote it off because here, now this will actually come
so
sitting here along with the, okay, let me correct it. So that will be k times k times 2 VGS minus VT the whole square. This is how it will come.
so the quadratic equation which I got is V out is equal to 5 minus
Uh,
0.75.
just hold on,
Okay,
let me write it down so that
Shrujan is showing.
Sujan is showing. Okay. Yes, Sujan. V out is equal to no, okay. 0.75 V naught square minus V naught into 1.5 VGS minus 0.5 minus minus sorry plus 5. That sounds correct. Okay. So now let's solve. How do you solve this? You have to do, there are only very few ways. One is minus b plus minus b square minus 4ac by 2a. That is the way it has to be done. But I think once you get this equation, I think it should be fairly simple to get that answer. So let me write the output equation. 0.75 p naught minus 1.5. So 1.5 VGS is going to be V in, correct? In minus VT, and then it is plus 5 equal to 0. Is that right? No, no, no. VT is also given, right? So I think that is also taken. So it must be V in must be V in minus 0.5 plus 5 equal to 0. Cannot be V in, sorry. It has to be V out only. Yeah, sorry, V out.
No, sir. That 1.5 into that will be VGS, right? VGS minus VTH. So that is Vin only, right?
VGS minus VTH. Oh yes, I saw, sorry. Yeah,
The
VGS only.
outside term will be V out.
V out is on the outside side. Okay, I did not. So there, here is a V out. See, let me tell you, do it this way. Okay. Put what is the V in value. We already know the last range, right? V is 3 volt. You need to know what is the values at 3 volt and 5 volt. See what are the values you are getting at these two from this V out. Let's, instead of solving the entire thing, let's do a short way. Looks like it is taking more time. So solving the entire, if you can solve the entire equation using a calculator, fine. Otherwise, that would be a short way. So take so minus B would be 1.5 Vi minus 0.5 plus minus B square. 1.5 Vi minus 0.5 whole square minus 4 AC. So A is 0.75, that is 3 by 4. So 3 by 4 into 5 into 4. So 4 will get cancelled. 3 into 5 is 15. So minus 15 divided by 2A. So 0.75 into 2, 1.5. So did you get that equation? So once you get this equation, let's substitute the values for V in that and get the output V out value. So first value will be 1.5 times V in, so that would be 1.5 into 3 is 4.5. 4.5 minus 0.5 is 4. So 4 minus 4 means it will be 4 plus minus square root of V square. 4 into square 16 minus 15, so that is 1. So square root of 1 is plus minus 1. So 4 plus minus of 1. So since they are 2 plus minus, you can just retain the, it will become plus minus, so plus minus only. So 4 plus minus 1 divided by, I think it was 1.5. 2A, yeah, 1.5. So 4 plus minus 1 divided by 1.5 will be the values. So 4 plus 1 is 5. 5 divided by 1, how much is 5 divided by 1.5? 3 times 10 times. So 10 by 3, so that will be around 3.3. Okay. So one end is going to be 3.3. Right. So it is 3.3 approximately. And what is the other side? Other side it is 4 minus 1, so that is 3. 3 divided by 1.5, that will be 2. Correct? So I have to put one more bar over here. So this is 2.0. So around 3.3. So since this was a quadratic equation, right? It is not a linear line. So this is as a quadratic relationship. So the quadratic, we go this way. Two. So this is somehow that it will probably look like. Okay, so looks like this line is also having a quadratic response, right? V0. This will also not be a straight line. This will also be a quadratic line. What do you observe in this one? This is not right because your current is going to have a negative term Vn. So the slope has to be on the opposite side. So slope will be in the opposite side. So these are the three
Sir,
ranges.
when the Vin, yeah, when Vin is 5 volts, the Vout is 0.77, right?
When V out is 5 volt.
V in is
When
5
V
volts,
in is
yes.
okay, that's why I asked. So it was like V in minus.
I am also getting 0.78.
V in, yeah, that actually has to make sense. V in minus 5. So 1.5 into 5 is 7.5 minus 1. So it will be 6.5. Yeah.
7.
That, yeah. So that will be. So 0.77 is what I think it should be getting.
Yes.
Okay. Or even close by is also is. So this graph.
And the maximum what I had calculated is 1.73 at 3.1 volts.
3.1 volt. What was it?
1.73.
Okay, so that means there is a break in the equation, is it? There cannot be a break, right?
Yes.
Can somebody confirm? So as of now, I will write it here and keep.
No, there will not be any break.
Then one of
There
the
should not
equations
be any
is
break.
not. Then one of these equations is not calculated correctly.
There should not. Curve will be
But
continuous only.
Yes, correct, right? So there has to be one of these equations is not done correctly in that case. So if he says it is 1.7,
It will be. It should be like from 0.77 to 3.5.
yeah, ideally. So that is why it's calculated 3.3. So let somebody confirm. Or let me just keep it, write it and keep it 3.3. Let somebody say a different number. Till then I will work it out as the same value. 0.77 less than V out less than 3.3. Yes, that
Sir,
is the
I
way it
have
has. You have a doubt, tell me.
like okay at 0.77 volt, whatever current I am getting is like 4.26 milliamps. Points.
Okay, come again. Oh, at V in equal to what value?
V in equal to 5 volt. V out
Hmm.
is 0.77 volt. That is what we have calculated. I have calculated 0.78 volt.
Okay,
Okay.
7.5.
For
Okay. The
for
current
that
value?
current value is coming out to be 4.2 something.
4.2. That's okay. 4.2 milli only, right?
Milliamp.
Okay. 4.2
Now
milliamp ID. So what is the higher range?
like from 1.5 milliamp it should come to this 4.2.
No, it should match in the equation. That is what I'm saying.
Match
Current
means
equation should match.
at maximum voltage at 5 volt current is 4.2 milliamps. So
Okay.
lower will start from 3 volt, and 3 volt we have already calculated there. So I am not calculating at 3 volt because
No, we
whatever
need to
we
see if the linear equation overlaps. We need to find out,
overlap,
right?
it
Yeah, you
should
have to
match.
either
But
say
okay,
less than or equal
I
to
have
or some condition it has to match.
correct, sir. So
So
now my
for that we
doubt
will
is.
have to see.
So now my doubt is if we plot like okay. Understood.
Understood, right?
Okay, what I was telling is, key my doubt was how in linear region current can be more than whatever we got in saturation, but that is for different value of VGS
Yes,
altogether. So
correct. That's right. That's why we
okay,
want to find out at the lower end also how much current is
correct.
going to come.
Okay, thank you.
Okay, I'm just getting a call. I'll be off in just 2 minutes. I'll come back.
Hello. Hello, Srijan. Fun.
Yeah, hello. Yeah.
Sure. No, I am getting V out as 3.33 and 0.77. Anyone? Hello.
Minimum V in you are choosing. What is your minimum V in?
V in minimum V in 3. For minimum V in is equal to 3, V out is 3.33.
Yeah, for minimum V in 3, it is 3.33.
Yes, yes.
Srinath, your mic is not on.
What is the current range we are getting? Hello.
Hello.
Hello, I
Okay.
didn't calculate the current. I didn't calculate. I'll have to calculate.
Okay.
Okay.
For me, I'm.
Actually, I want to add here. Hello.
Tell me, tell me.
See, once you calculate voltage range,
Ah,
calculate range, current range, we need not to calculate by MOSFET current equation. We can directly put that
yes,
voltage
yes.
range divided by R.
Yes, yes. That one also we
So,
can.
okay.
Yeah, yeah, the
Just one
V
way
out
you
by
have
R,
to.
V out by R will give us.
Just so just that thing. Can we do that way?
Yes, yes. I think I have done using MOSFET equation. We can
Yeah, for
continue with.
Hmm.
this
Yes,
region you can do. For the saturation
I
region you
think we
couldn't.
can. Why cannot at those particular value voltage when we have given? That's what I am trying to. Okay, see. Okay, see. At in saturation region, my voltage is at 1 volt. V out is 4.9. So 5 minus 4.925. How much it is coming?
5 minus 4.925.
925.
0.05.
See, 75 microampere is not it coming? And then 3.5 volt, then 5 minus 3.5 volt divided by 1K is 1.5 milliamps.
Yes, yes. You're getting right that one.
So are you
You
getting
had
my
calculated
point?
the voltage using the current. You had not done it the other way around.
No. Just for filling this table, I am telling.
Yes,
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 yes.
for
We can
this,
do like that.
yes.
Not a problem. I guess.
Uh, that much only.
So the information that is coming in this table, the graph will look something like this. Okay, so doesn't this look a little weird to you people, that from cutoff it is going to saturation and then coming to linear?
Yeah, this is because the drain terminal is at very high potential in the initial stage. Thus,
Yes.
once the device turns on, it goes into saturation instead of going into a linear region, I would say.
Exactly. Very good. So that is the correct answer. So that is the intuition that you need to get. That sometimes your decision making is not limited only by one variable. There are other variables also will affect. Now, just imagine what will happen. So, what do we see here? If you take out the saturation region portion and only use a cutoff and linear region, both the cutoff and linear region are having uh, current equations and cells. So this can be act as a switch, obviously, like we all know. But for amplifier action, you need it to be in saturation region. So if you take out the portion of the saturation region, you are keeping it in acting it like a switch, where either the current is fully off or the current is fully on. You're getting the two portions visually. Now to get an amplification in this one, what is expected is, just a minute, I'm getting a call again.